Okay, in this lesson, we're going to take a look at adding and subtracting radicals. So we know how in the last lesson we said we can't just add and subtract radicals by adding or subtracting the radicands, right? We can't just say if we have the square root of 16 plus the square root of 9, it's the same as 16 plus 9 and then take the square root of it. It's not the same number. So the first thing that we do is we take some possibilities and we put them into our calculator to see which are true. So if I take the square root of 2 plus 5 root 2, is that the same as 6 root 2? Well, I'd put the left side of my calculator, the right side of my calculator, and then if they wind up coming up with the same number, then it's true. And in this case, yes, it is. If I take 4 cube root 5 minus 3 cube root 5, hit enter, and then put in negative 3 cube root 5 and hit enter, I get the same number again. If I take 5 root 8 and 2 root 8 plus 7 root 8, then I put in 10 root 8 in my calculator, they are the same. Perfect. When I take 7 root 5 plus 7 cube root 5, does it make 14 and the fifth root of 5? No, doesn't work. When I take cube root of 3 plus the cube root of 2, does it make the cube root of 5? No, and that one we should have already known from the previous lesson. It doesn't work if you just do it with the radicands. So, based on what we see here, what's the rule? Well, the commonality with examples 1, 2, and 3 is that the radicals can be added or subtracted if they have the same radicand and index. We can see that it didn't work with example 4 because this is a square root and this is a cube root. We can see that it didn't work with example 5 because the radicands were not the same. But if we want to simplify this idea, if I take that first example, the square root of 2 plus 5 root 2 is equal to 6 root 2. What if I just said that x is equal to the square root of 2? Then this would be the same as 1x plus 5x's is equal to 6x's. And we know from our polynomials that that's 100% true. If they're all x, they're all the same number, then I just add their coefficients. 1x plus 5x is equal to 6x's. The same thing is true with the radicals. If it is the exact same radical, or the square root of 2, then if I'm adding however many square root of 2's, then I can say how many root 2's do I have. So when I put this into practice, if I have 8 root 7's minus 3 root 7's plus 15 root 7's, then how many root 7's do I have? Well, I have 8 minus 3 plus 15. I have 20 root 7's here. When I get to the next example, if I have 18 fifth root of 10's plus 12 fifth root of 10's minus 7 fifth root of 10's, then I'm trying to figure out how many fifth root of 10's I have. 18 plus 12 minus 7 is 23. Even if I add a variable into the mix, doesn't change it. The square root of x is still the same as the square root of x. So if I have 5 root x's minus 4 root x's, I'm left with a singular root x. Now, if I plug these into my calculator, the square root of 2 plus the square root of 8, and then put in 3 root 2 That's true. It does work. If I put in 5 root 12 plus 6 root 48, is that the same as 34 root 3? That is also true. Does that break our rule that we had from the first one where they had to have the same index and the same radicand? Yes. But we can see once we simplify them, they're actually equivalent radicals. So if I took in the first example, the square root of 2 plus the square root of 8, the square root of 8 is not in simplest form. I can simplify that to the radical 2 root 2. And once I've simplified it, they are the same radicals, root 2 and root 2, which means that they're just 3 root 2's. When I take the second example, once again, these are not simplified. Now, when I simplify these ones, what I'm going to do is I'm going to leave the coefficient, and when I simplify it, I'm going to put it in brackets just to make sure I multiply it out properly again. So what do they simplify to? Well, the square root of 12 is the same as 2 root 3's. The square root of 48 is the same as 4 root 3's. Now I need to make sure that I multiply my coefficients, expand those out properly, and what that's going to give me is 10 root 3's and 24 root 3's. Now they're identical radicals, root 3 and root 3. I have 10 of them and then another 24. I have 34 root 3's, which is exactly the answer that it gave me. So if I'm writing an expression in terms of a single radical, the first step is you have to be able to simplify every radical that exists. You're going to simplify it as far as it will go. So the square root of 80 minus the square root of 20, the square root of 80 is 4 root 5. Minus square root of 20 is 2 root 5. Now be careful with this because if you don't simplify them properly, you're going to lose all of your marks because it's assumed that in grade 11, you already know how to simplify these radicals properly. I know we did a review on it, but you're expected to be able to simplify them accurately every single time because it's a concept you've already learned. Then it's just a matter of combining them. 4 root 5 minus 2 root 5's, I'm left with 2 root 5's. In the next example, if I have the cube root of 80 plus the cube root of 270, well, that's going to be 2 in the cube root of 10 when I simplify it. And the second one is going to be 3 in the cube root of 10, which is going to give me 5 times the cube root of 10 as my answer. Now we can have multiple of these. Doesn't really make a difference. In this case, I have 3 terms, so I just need to simplify all 3 of them. Now remember, if they already have a coefficient, do 7 bracket and then simplify. So 7 bracket square root of 27 is going to be the 3 root 3. Minus 3 bracket square root of 75 is 5 root 3. Plus 2 bracket square root of 147 is 7 root 3's. I'm going to make sure that I multiply all these out properly. 7 times 3, negative 3 times 5, and 2 times 7. And I'm going to get 21 root 3's minus 15 root 3's plus 14 root 3's. 21 minus 15 plus 14 gives me 20 root 3's.